All right, in this video, we're going to talk about just a short review on scientific notation, what it's all about, because Section 3B does have some concepts in there that are related to scientific notation. So that's the first thing I'll do is cover the short review on scientific notation and how to convert from from ordinary notation or standard form to scientific notation, and also from scientific notation to standard form. Also, we'll talk about how to multiply and divide decimals or divide expressions written in scientific notation, and add and subtract with scientific notation. All right, let's talk about converting scientific notation. To convert a number from ordinary notation to scientific notation, there are two steps. Number one, you want to move the decimal point to come after the first non-zero digit. And then step number two, for the power of 10, you're going to use the number of places the decimal point moves. The power will be positive if the decimal point moves to the left and negative if it moves to the right. So here's some examples of that, like 3.3042 or 3042 to be exact. We want to write that in scientific notation. So that means I need to move the decimal point 3 places to the left, because I want the decimal point to be behind the very first non-zero digit from left to right, if you're reading it from left to right. So the decimal point would be behind the 3, so it'd be 3.042. Now, in reality, we moved the decimal point 3 places to the left, so that means the exponent for the power of 10 would be 3. So 3042 in scientific notation would be 3.042 times 10 to the third power. And then next we got 0.00012. In this case here, we want to convert that to scientific notation. In this case, we need to move the decimal point behind the first non-zero number. So the decimal point needs to be behind the 1. That means I need to move this decimal point 1, 2, 3, 4 places to the right. And since I moved the decimal point to the right 4 places, the exponent for the power of 10 would be -4. And the first part of that scientific notation would be 1.2. So 0.00012 in scientific notation would be 1.2 times 10 to the -4. And then 226 times 10 to the second. Now, the first part, which is the 226, is not in scientific notation. We need to write that in scientific notation. I will tell you that in scientific notation, the first part of that answer has to be a number that is at least 1 but less than 10. This is bigger than 10. That 226 is bigger than 10. So we need to put a decimal point behind that very first 2. So it'll be 2.26. And there are 2 numbers after that decimal point. So it'll be 2.26 times 10 to the second. But we also got 10 to the second that we're multiplying here. So when you multiply powers of the same base, you have to add your exponents for the base of 10. So it'll be 10 to the 4th. So 226 times 10 to the second will be 2.26 times 10 to the 4th, written in scientific notation. Next, we'll look at converting from scientific notation. And it's going to be this: to convert a number from scientific notation to ordinary notation or to standard form. Again, you have 2 steps. Number 1, the power of 10 indicates how many places to move the decimal point. Move it to the right if the power of 10 is positive, and move it to the left if it is negative. And then second, if moving the decimal point creates any open places, you'll fill them in with zeros. So like in these few examples here, we got 4.01 times 10 to the second. Well, the exponent for the power of 10 is going to be 2, so that means I need to move the decimal point in 4.01 2 places to the right. So this will end up being 401, or just appropriately read 401. The next one, 3.6 times 10 to the 6. Well, the exponent for the power of 10 is 6. That tells me in 3.6, I need to move that decimal point 6 places to the right. Okay, I only got room to move the decimal point 1 place. I need to move it 5 more places. And in order to do that, I'm going to need 5 extra zeros behind the 3 and the 6. So 3.6 times 10 to the 6 would be 3,600,000. And then the last one, 5.7 times 10 to the negative 5. Well, the exponent there is negative 3. 5.7 times 10 to the negative 3. That exponent there is negative 3, so that means I need to move the decimal point 3 places to the left. I only got room to move it over 1 place to the left. So for me to move it over 2 more places, I'm going to need 2 zeros in front of the 3 and the 5 and the 7. So 5.7 times 10 to the negative 3 will be 0.0057. Okay. All right, next is multiplying or dividing with scientific notation. Multiplying or dividing numbers expressed in scientific notation simply requires operating on the powers of 10 and the other parts of the numbers separately. So in this example, if I can get to it, here we go. Here's a couple of examples of that. One for multiplication and the other one is for division. 6 times 10 squared times 4 times 10 to the 5th. So here we have to multiply the numbers that are in front of the multiplication symbols. 6 times 4, and then we have to do the powers of 10, multiply those. 10 to the 2nd times 10 to the 5th. So we multiply 6 times 4, that's 24, and then we multiply 10 squared times 10 to the 5th. Here we're multiplying powers of the same base. We bring over the base of 10, add the exponents of 2 and 5, you get 10 to the 7th. So here we got 24 times 10 to the 7th. But that is not written in scientific notation. If you recall, scientific notation is a number that is at least 1 but less than 10 multiplied by some power of 10. So we need to write 24 in scientific notation. So we need to put the decimal point behind the very first non-zero digit. So the decimal point will have to go behind the 2, which will make that 2.4 times 10. And there's only one number behind the decimal point, so that exponent for 10 would be a 1. And then we got 10 to the 7th to deal with. So that's times 10 to the 7th. So here we'll bring down the 2.4, multiply powers of the same base by adding your exponents. So this will be 10 to the 8th power. So the final answer there will be 2.4 times 10 to the 8th power. All right, and then next we got 4.2 times 10 to the negative 2 divided by 8.4 times 10 to the negative 3. I'm sorry, negative 5. It's hard to read here. So here we divide 4.2 by 8.4, and then we divide 10 to the negative 2 by 10 to the negative 5th. Well, 4.2 divided by 8.4 will be 0.5. Here we're dividing powers of the same base, so we bring the base of 10 and subtract negative 2 minus a negative 5, which is actually negative 2 plus 5, which will give you 3 for the base of for the exponent of 10. So I have 0.5 times 10 to the negative 3rd power. Again, this part right here must be a number between at least 1 but less than 10. So To do that, I need to move this decimal point one place to the right, so the decimal point would be behind that first non-zero digit. So this is 5 times, and I only moved it one place to the right, so that means 10 to the negative 1. And then times 10 to the third. And then, of course, bring down the 5 and then add your exponents for 10. So it'll be 10 to the positive 2 power. So the final answer there will be 5 times 10 to the second. Now note that in both examples, we first found an answer in which the number multiplied by a power of 10 was not between 1 and 10. So here we then follow the process of converting the final answer into scientific notation. So keep in mind, scientific notation is where the first part must be at least 1 but less than 10, and the other part has to be multiplied by a power of 10. Okay, now for adding and subtracting with scientific notation. Here we have to write the numbers in ordinary notation or standard form, excuse me, below, and then add and subtract. So here we got 3 times 10 to the 6 plus 5 times 10 squared. Now we need to convert 3 times 10 to the 6 in standard form, which will be 3 million, because that 6 tells me how many zeros are there after the 3. So it'll be 3 with 6 zeros, 3 million. 5 times 10 to the second, the exponent there for the power of 10 is 2. Well, 10 squared is 100, so 100 times 5 will give you 500. And then we convert, well, we add the two together. 3 million plus 500 will give us 3,500,000. And then we convert to scientific notation by putting the decimal point behind the very first non-zero number. And the very first non-zero number is the 3, so that decimal point goes behind the 3. And then we got 0005. We write that down. Do not worry about these zeros on the end. Times 10 to the, well, if I put the decimal point behind the 3, that means that there are 6 digits behind it. So it'll be 10 to the 6. So my final answer there will be 3.0005 times 10 to the 6. All right, now we got 4.6 times 10 to the 9th minus 5 times 10 to the 8th. Okay. Okay. All right, now for the 4.6 times 10 to the 9th, we got the 4 and the 6. We need to move the decimal point 9 places to the right, so we can only move it 1 place to the right, but we need to move it 8 more places. So that means we need 8 zeros behind the 4 and the 6. So this will be 4,600,000,000. And then minus for 5 times 10 to the 8th power. We bring over the 5, but that means we need to add 8 zeros behind it. So it'll be 500,000,000. Subtract 500,000,000 from 4,600,000,000, you'll end up with 4,100,000,000. Now, if we were to write that in scientific notation, that means I need to put the decimal point behind the first non-zero digit, which is a 4. So it'll be 4.1 times, and notice I have 3, 6, 9 numbers behind it, so it'll be 10 to the 9th. So the final answer will be 4.1 times 10 to the 9th. Okay. Now, when both numbers have the same power of 10, we can factor out the power of 10 first and then simplify. Like in these two examples here, 7 times 10 to the 10th plus 4 times 10 to the 10th. Notice 10 to the 10th is in both of these expressions here, so we can factor out the 10 raised to the 10th and then just add 7 and 4 together. So 7 plus 4 is 11. So it'd be 11 times 10 to the 10th. But of course, 11 needs to be written in scientific notation and then simplified. Putting the decimal point behind the first one, there'll be 1.1 times 10, and we have to move the decimal point one place to the left, so that exponent will be 10 to the first, then times 10 to the 10th. And 10 to the 1 times 10 to the 10th ends up being 10 to the 11th. So my final answer there will be 1.1 times 10 to the 11th power. And 2.3 times 10 to the negative 22nd minus 1.6 times 10 to the negative 22nd. You can see here the 10 to the negative 22nd is common in both of these. So we can pretty much factor 10 to the negative 22nd out. You'll be left with 2.3 minus 1.6. And 2.3 minus 1.6 will be 0.7 multiplied by 10 to the negative 22nd power. But here we need to convert 0.7 into scientific notation. Here I need to move that decimal point one place to the right. So it'll be 7 times 10 to the, and since I moved it one place to the right, that exponent will be -1. And then times 10 to the negative 22. And if you add your exponents for the powers of 10, the final answer there will be 7.0 times 10 to the negative 23rd power. Okay. Now on the next page, we're going to look at some examples of just what I just got through talking about. So starting with number 1, we want to convert each of the following numbers from scientific to ordinary notation or standard form, as some textbooks say, and then write its name. So in part A, we got 5 times 10 squared, or 5 times 10 to the second. Well, the decimal point is understood to be behind the last digit in the whole number. So in this case, we have 5 point, and then that exponent for 10 will be 2. That tells me I need to move this decimal point 2 places to the right. And I have to add 2 zeros to that. So 5 times 10 to the second will be 500, written in standard form. So to answer that, 5 times 10 squared would be this number, 500, 500. But in words, we're going to write that as 500. 500. All right, now part B is 4.4 times 10 cubed. 4.4 times 10 cubed. Well, in this case here, the exponent for 10 is 3. That tells me I need to move this decimal point in 4.4, 1, 2, 3 places. I need to add 2 zeros to that. So 4.4 times 10 cubed in standard notation would be 4,400. And then we write that number in words. So it'd be 4,400. Now part C, 7 times 10 to the negative 4. 7 times 10 to the negative 4. Okay. 7, the decimal point is behind that last digit in that number. The exponent for 10 is -4. So I need to move this decimal point in the 7, 1, 2, 3, 4 places. That would mean I need to put in front of the 7 3 zeros. So I have 0.0007. So 7 times 10 to the negative 4 would be 0.0007. Now, the way we're going to have to read that is this. Right after number 7, using words. The place value position, the name for this will be the place value position of the last digit. So in this case, this will be tenths, hundredths, thousands, 10,000s. Okay. And finally, part D, 2.1 times 10 to the negative 6 power. And the exponent for the 10 is -6. That tells me I need to move the decimal point to the left 6 places. So here I'm going to move this decimal point 1, 2, 3, 4, 5, 6. That would mean I need 5 zeros in front of the 2 and the 1. So 2.1 times 10 to the negative 6 will be 0.00000021. Now, the way we write that, we're going to read this as 21 with the place value position of the last digit as its name. So this will be tenths, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions. Okay. So that was number 1. Now, number 2, we're going to go the other way. We're going to write each of the following numbers in scientific notation. Like in this case here in part A, 550. Now, the way we have to write this in scientific notation is this. We need to put the decimal point behind the very first non-zero digit in that number. So the decimal point will be behind the very first 5 here. So this will be 5.5. Then that's going to be multiplied by 10. And if I put the decimal point behind the first 5, I need to count how many digits are there behind it. That would tell me what the exponent for 10 would be. There are 2 numbers behind it. So it would be 10 to the second. So 550 in scientific notation would be 5.5 times 10 to the second. Okay. All right, part B, 0.0105. And I want to write that in scientific notation, 0.0105. So in this case here, I need to place the decimal point behind the very first non-zero number, or non-zero digit, which is going to be the 1. So the decimal point needs to be behind the 1. So I'm going to end up with 1.05. That's going to be multiplied by 10 to what power? Now I move to the right. So that means I have to use a negative exponent for 10. And I moved it 2 places to the right because the original decimal point was here. The new decimal point will be here. That means that there are 2 digits in between it. So it'd be -2 for 1.05 for the power of 10. So 0.0105 in scientific notation will be 1.05 times 10 to the -2. And then 7,012.3. This part C. 7012.3, 7,012.3. And I want to write that in scientific notation. In this case, I need to put the decimal point behind the very first non-zero digit from left to right. So that decimal point needs to be behind the 7. So I'm going to have 7.0123 times 10. And I went from this decimal point to this decimal point here. I went to the left 3 places. So the exponent for the 10 would be 3. So it'd be 7.0123 times 10 to the 3rd. Okay. So here, that's problem number 2. All right, number 3. We're going to do a little multiplication, addition, and I think division. So here we're going to do the following operations without a calculator, and be sure to express your answers in scientific notation. You may round your answer to 1 decimal place, as in 3.2 times 10 to the 5th. So here in part A, we got 3 times 10 to the 7th times 2 times 10 to the 8th. And here I want to simplify this. Now, this is just a multiplication. So what I can do here is multiply 3 times 2, and then multiply that by the powers of 10. 10 to the 7th times 10 to the 8th. So in this case here, if I do 3 times 2, that's going to be 6 times, and then multiplying the powers of 10. Multiplying powers of the same base means I can add the exponents. So I'll bring the 10 down, add 7 and 8 together, you'll get 15. And as you can see, it is already in scientific notation. So my final answer there will be 6 times 10 to the 5th. All right, part B, we got 8 times 10 to the 7th. And this is plus 2 times 10 to the 6th. Now, what I'm going to do here is write these out in standard form or in ordinary form. So for 8 times 10 to the 7th, I have the 8. That 10 to the 7th, that exponent of 7 means I need 7 zeros behind the 8. And then for 2 times 10 to the 6th, well, bring down the 2, that 10 to the 6th, that 6 tells me I need 6 zeros. So it'll be 1, 2, 3, 4, 5, 6. So that means I got 800 million plus 2 million. And if I add those two together, it's going to be 802. I'm sorry. With 7 zeros, that should be 80 million. And 8 with 7 zeros, that's 80 million. Plus 2 million. So it'll be 82 million. Okay. Now that 82 million needs to be written back in scientific notation. So I need to put the decimal point behind the first non-zero digit, which is your 8. So here I'm going to have 8.2 times 10 to some power. Well, if I put the decimal point behind the 8, there are 7 digits behind it. So it'd be 8.2 times 10 to the 7th. Okay. Now in part C, we got 4 times 10 to the 14th. And that's a division, so I'm going to write this a little bit different. That's going to be divided by 2 times 10 to the 4th. So I'm writing it like this, because you're going to see the division that we have to do here. Okay. So what I'm going to do here is divide 4 by 2. And then that's multiplied by 10 to the 14th divided by 10 to the 4th. Well, 4 divided by 2 will be 2 times, here I'm dividing powers of the same base. So this time I'm subtracting my exponents. So it'll be 10 to the 14 minus 4, which is 10. So the final answer there will be 2 times 10 to the 10th power. All right, and finally, number 4. Here we're going to compare the numbers in each pair and give the factor by which the numbers differ. So in part A, we got 10 to the 34th 10 to the 34th and 10 to the 27th. Okay, so we want to find out 10 to the 34th is how many times as large as or smaller than 10 to the 27th. Okay. All right, in this case here, this is what I'm going to do. I'm going to take that 10 to the 34th, divide that by 10 to the 27th. When you divide powers of the same base, of course, you're going to subtract exponents. So bring the 10 down, subtract 34 minus 27, you'll get 7. So this tells me it is a positive exponent for the power of 10. So it'll be 10 to the 7th, meaning that 10 to the 34th is 10 to the 7th times. And since it's positive, it's going to be as large as. As large as 10 to the 27th. So to complete that sentence, 10 to the 34th is 10 to the 7th as large as 10 to the 27th. Part B, 10 to the 17th is how many times either as large as or smaller than 10 to the 27th. Well, again, you're dividing powers of the same base. You're going to subtract your exponents here. And the way you'll set this up would be 10 to the 17th divided by 10 to the 27th. All right, we're subtracting exponents because our bases are the same. Bring the 10 over. Now, if you do 17 minus 27, you're going to get negative 10. Okay. So to answer this question, you're going to say 10 to the 17th is, and actually we're going to use positive exponents here, 10 to the 10 times. But since it's negative, we're going to say 10 to the 10 times smaller than 10 to the 27th. Smaller than because we got a negative exponent for the base of 10. So it'd be 10 to the 10 times as smaller, well, 10 to the 10 times smaller than 10 to the 27th for that 10 to the 17th. And then part C, 3 billion compared to 3 million. Let's write 3 billion as 3 with 9 zeros. That's how we write 3 billion. On the other hand, 3 million is 3 with 6 zeros behind it. Okay. Here I'm going to divide out a period of zeros like this. And then 3,000 divided by 3 ends up being 1,000. Now, 1,000 in scientific notation would be this, 10 to the third. Okay, because 1,000 is 10 times 10 times 10, which is 10 to the third. So 3 billion is 10 to the third times as large as, because our exponent for the 10 is positive, 3 million. Okay. All right, so that does conclude this short review for section 3B, and that's working with scientific notation. This will assist with the lesson in section 3B dealing with putting numbers in perspective.